Of course, it's not like that because it's a vector, but you know, sort of to speak quickly. And so we are going to consider a function wrong for the moment, but we'll fix it immediately. F of r, which is a scalar. What's that? No. F is this same function that we had before. I'm going to show you because basically, look what I'm trying to do. I already realized that there is a function f whose gradient is the electric field. What is a gradient? Is a derivative, sort of, right? And so if the electric field, even though it's a vector, sort of goes like 1 over r squared, and that is a correct statement because we know from Coulomb's law that the electric fields drop like 1 over r squared, so each term in this sum drops like 1 over r squared. So I'm trying to see if I can come up with a function that drops like 1 over r, yes, and it's a scalar. Why? Because when I take derivatives with respect to something, what is the derivative of 1 over x? What is the, well, this is a negative, that's why I'm going to fix it later, but the derivative of 1 over x is minus 1 over x squared. Okay, so if I'm looking for a simple scalar function, the guess 1 over x is the simplest thing, and we can try, and it turns out that it will work with a very tiny fix. So I'm proposing to use this f that looks like 1 over r, and we'll take the gradient of that function. Okay, so in particular, for example, let's try to take the derivative of f with respect to x and see if we are lucky, or if we're not, maybe we can fix it. Okay, so what is the derivative of f with respect to x? So, well, I don't see x here, so let's make it explicit. So it's going to be a constant 1 over 4 pi epsilon 0, then the derivative with respect to x, because it's a sum, I can take the sum out, sum qi, and then the derivative with respect to x of 1 over r minus ri. Okay, so it's not yet clear how to take the derivative, so let's make this term explicit in terms of, let's, you know, show the x so we can take the derivative. So this is going to be 1 over 4 pi epsilon 0, sum in I, qi, and then the derivative with respect to x. Okay, and now what is that? That thing is that the magnitude of that is x minus xi squared plus y minus yi squared plus z minus zi squared, and then we need to take the square root of the whole thing. And now we see the x there. Good? Okay, and so now that I show you the expression, you tell me what is the derivative of that. So all those constants still stay, that they don't bother us. Okay, so what is the derivative of that big expression?
The one that you cancel, it's going to be the integral, the derivative.
We are doing the derivative with respect to x. That's what I want. So we need to do the chain rule. Go ahead.
2x over the whole thing to the minus to the 3x.
Okay. Very good. Yeah. So let's do it. So the derivative with respect to x of this, we can actually see that this square root is equivalent to a big thing to the minus 1/2. And so we take the minus 1/2, and this thing becomes minus 3/2. Okay, so let's do it in pieces. Okay, so the first thing that we get is a minus 1/2. Then we get to the minus 3/2, so it's a 3/2 at the bottom, like you tell me, and so we get x minus xi squared plus y minus yi squared plus z minus zi squared, and then that thing down here to the 3/2. That's one thing. And then you told me that you use the chain rule, that because we are taking the derivative with respect to x, the y and z terms are not affected, those are 0, and this one will give us a 2x minus xi.
Yes.
Wait. What's that?
Dx.
dx? No, dx. This is derivative, so there is no differential, okay? So, okay, so the only thing is that we have a half here, okay, that cancels that too. But other than that, so it's just a straightforward derivative. And okay, turns out that the thing at the bottom we can undo, and is nothing but the magnitude of r minus ri cubed. We can do that again. So this is only for shorthand notation. So the 2's cancel out, and there is a minus sign, an extra minus sign, so we get a minus 1 over 4 pi epsilon 0 sum in I qi over r minus ri cube. Okay, that's what it is at the bottom. And then we get an x minus xi. Okay. So without the minus sign, what we got? Perfect. Okay. So if we look at the electric field that we have up here, then what we just obtained is the x component of the electric field, because it's exactly, everything is exactly the same thing, only that we have an x minus xi here instead of the r minus ri in general. So that is clearly the x component of the electric field, negative. Okay, we got then this very nice result that this is minus ex. So only with the exception that we made a mistake with the sign, this derivative of this explicit function with respect to x gave us the x component of the electric field. So look at this. Okay, so we'll fix the sign in a second, but basically I showed you before that there existed a function f so that when you take the gradient you get the electric field. And now we found what that function is, simply because the structure of the field is relatively simple. So how do we deal with that sign? Okay, so this is a question of convention, and so what we got here is, if we did the same thing for the y and z component, we could write this, that the gradient of this function that we just obtained explicitly, this expression here, is not e, but is minus e. Okay, so clearly then this function f is not the same that I had before, because now I have a negative sign. It doesn't matter. So this function that I just wrote here is called the electrostatic potential, and the letter that we use is V for that, okay, which we'll see later on that that's in some cases is connected with the voltage, with experimental voltages, okay? So, okay, but how do we deal with this negative sign? Well, very easy. The electric field is minus the gradient of V. It's an arbitrary choice to put a minus sign, because if you have a function f, minus the function is another function anyways. Okay, and so now we mess here and use the definition here of the electrostatic potential. Okay, and so the important equations that we have so far are this one here for the electrostatic potential, that one up here for the electric field that we had before, and the connection between the two, that the electric field can be obtained as minus the gradient of the electrostatic potential. Now, again, I repeat, just to make sure that we communicate, the negative sign is absolutely arbitrary. absolutely arbitrary. We could have chosen a plus, no problem. But, okay, so this is called the electrostatic potential. Okay, so, I repeat that a very, very big advantage of solving problems of this type practically is that if we can actually write them in a way that we can solve for the potential V instead of the electric field, then it's mathematically much, much easier because we need to find only a single function instead of three. Okay? So we are going to deal with examples of that many times in the course, and there are going to be methods, different methods we are going to develop to compute V, and eventually once we are done, we take the gradient to obtain the electric field. Okay? So that's the story. Okay, clearly, and I'm not going to do it for you, you will think yourself about those things, but this is symbolic, okay? Meaning that I have a set of charges I that are discrete, but clearly if my charges are located on a line or on a surface or on a volume, then I can use lambda densities or sigma densities or rho density like we learned before, and we can write this same expression in terms of integrals, no problem, same as we did with the electric field. So I don't need to write that, you know. Okay, so if we need that, we will use it, and we will. Okay, so great. So we have all these nice properties, so we have then, we proved that the curl of the electric field is equal to 0, and then we proved that the electric field can be the gradient. Okay, so those things we save for later because those are going to be related later on with Maxwell's equations. Okay? Okay, so now I want to formalize a little bit the issue of how fields are seen when we look at a distribution of charge from far away, which is formally called multipolar expansion. Okay, let me explain that. Okay, so one thing that I emphasize in the few examples that we did before is what is the behavior of the electric field when we look at it from very far away. Okay, and so there were two nice examples because the charge distribution was confined to a certain region of space. For example, in the case of a charged ring, we have the charge on a ring, and clearly outside of a certain region of space there is no charge anymore. Same thing when we had a disk of charge. And in both cases, we proved that when we move very far away, the electric field drops like 1 over the distance squared. Remember? Okay. So, and the argument, the intuitive argument for that result is that when we are very, very far away from an object, we cannot see the structure anymore, and the only thing that we can detect is the overall charge, and we see a very tiny point very far away, so clearly we recover Coulomb's law. Okay? So, but there is a more general statement of that result, which is the Coulomb's term is called a monopole term. But then we have dipole terms and quadrupole terms, etc., and those names are different terms of the so-called multipolar expansion. So what is going on? What's going on is that, for example, if we have a ring of charge or a disk of charge, just because we did those, when we are very far away, we will see 1 over 4 pi epsilon 0 q over r squared behavior for the field. But as we get closer, we have the expressions for those fields that we computed in class, and we see the Coulomb expression is not true anymore. We had a more complicated expression for the field. Okay, so so when we have an extended distribution of charge, some other things happen besides the Coulomb law. Okay, but it turns out this is a big problem in electricity. There are still today many open problems as we speak 2018, even though the field exists for so many years, and some of them very basic and applied. For example, if you have a distribution of charge in this has applications in coping machines or in designing new materials. If you have a distribution of charge in a certain region, yes, and you use an instrument to measure, for example, the electric field around that region, what charges produce that electric field. And so even from a mathematical point of view, not forget about an applied physics problem, but even from a mathematical point of view, this is a very, very, very complicated problem. Okay, and so if you are interested to know more about it, I'm happy to talk with you about this after class. But the thing is that the quick answer is that it is close to impossible in many situations to come up exactly to where the charges are. Okay, even if you have information about what effect they produce. And so for that reason, there are some type of information that is useful to have about any distribution of charge. And so, for example, one nice example is that let's say that you are trying to study a certain substance, maybe a liquid, okay, and you are trying to figure out what is the quantum mechanical response of the system, whatever. And so then the atoms in that system will have a charge distribution, right? There's a proton, there are electrons around that center, that positive center, and what could happen is that, for example, that negative cloud of electrons is symmetric around the nucleus, or it could also be that the cloud of electrons is a little bit shifted with respect to where